Here's an example of thinking with classical relativity. What I've drawn is basically a highway that runs north-south. And on the right-hand side, I've got three cars all headed north at 70 miles per hour. And on the left-hand side, I've got the opposite direction of traffic, and they're moving slower. Each of these cars is moving at 50 miles per hour towards the south. So you can see that I have a bunch of velocities. I'm going to talk about relative motion by talking about particular cars. So let's say that this car is car A, this car is car B, and this third car is car C. So I'm not going to consider the other three cars. So I've got these three cars. So pretty obviously, we're talking about motion, so let's talk about velocity. And so, for example, the velocity of car A looks like it's 50 miles per hour. That's the speed of the car, and that car is heading southbound. So let's give it a full-fledged vector value. So I've got the speed and the direction. So this is the velocity of car A, but it really is relative to the ground, right? So this designation of the velocity is measured relative to some other object. So this is the velocity of object A, or car A, with respect to the object called the ground. So let's call the ground capital G. So really, this thing is the velocity of car A relative to object G, or the ground. So let's say this is the velocity of car A relative to the ground. So relative to object G. This is a notation, and this is the notation that I tend to use, but I always have to explain it. Yeah, so it makes it clear what I'm talking about, and in some sense, who's making the measurement. So you might say that this notation is ground G measures car A's velocity, right? And this is what's meant by the velocity of A relative to G. Velocity of A relative to G. Okay, so another example is the velocity of, say, car B relative to G is 70 miles per hour towards the north instead, right? Yeah, so, and I want you to notice, though, that, so this is kind of simple, right? So that's the velocity of B. And there's a third one for fun, the velocity of C relative to G is actually equal to the velocity of A relative to G, which is 50 miles per hour south. All right, so no big deal. This is kind of easy stuff, right? Easy stuff. We are talking about velocities of objects relative to other objects, though. And this is where, yeah, this notation actually is ultra convenient and makes the ideas clear. Yeah, it's an organization. Right? So we can be very, very clear about what we're talking about. Okay, so what I'm going to show you next is what's some people call it, I'll call it velocity addition. And let me just put in that this is classical velocity addition. right? Sort of the purpose of this sort of video is to introduce the idea of relativity. And we are going to talk in this video just about the classical version. The Einstein version, so classical, not the Einstein special, right? Special relativity is a different beast and it has a different velocity addition, but this notation is convenient also for Einstein special relativity. But anyhow, velocity addition, it comes with a formula, and I'll write it this way. The velocity of object A relative to object B is equal to, this is pretty cool, it's the velocity of object A with respect to some third object x plus the velocity of the object x relative to the object B that's mentioned over here. And this is the velocity addition formula, and it's a big deal. So this is a big deal, so let me put a big star next to it. Another big deal that comes up is to note the following thing. If, for example, I'll just write it. So notice that if you have the velocity of one object relative to another, so these are just, some arbitrary objects, x and y. So this is the velocity of object x measured by object y, or relative to object y. This is equal to the opposite of how x measures y's velocity, right? If you notice, check out velocity of A relative to B. Can you see that B says A is heading downwards, but A says B is heading upwards? They have opposite relative velocities. Or I'm not sure I said that the best way, but this right here is also a really important thing to consider. That you're going to pick up a minus sign if you switch the order of the indices, right? If you switch the labels. So the order of labels is important, right? So this big deal. All right, so let's move on. So I've given you this, we've just talked about this velocity addition formula. And we also have this consideration here about the order of the labels being really important. I'd like to check if I have velocity at A and velocity of B with respect to the ground, maybe I could use x as the ground. So let's say that what if x equals the ground g? Then what we can get is this velocity of, say, car A with respect to car B. So these things are going like this, but if you were an observer, if you're sitting in car B and you watch car A go by, then as you travel along, say you're traveling along at 70 miles per hour towards the north, you'll look over and you'll see, you won't necessarily detect your own motion. What you're going to do is you're going to look at how fast A passes you. So A passes you very, very quickly. And I bet you've got a gut instinct that A travels past B at 50 plus 70 miles per hour, 120 miles per hour. So we have a gut instinct that the velocity of A with respect to B at least has a relative speed of 120 miles per hour, right? This is our guess. But let's use the velocity addition formula to get this. And what's more is we're going to get a vector designation because these are velocity arrows, right? These are velocity vectors. So the velocity addition formula says that v, the velocity of A relative to B, is equal to the velocity of A relative to the ground plus the velocity of the ground relative to car B. So using this fact here, the order of the labels, if you switch the order of the labels, you pick up a minus sign. So let's rewrite this. This is the velocity of car A relative to the ground plus the opposite of the velocity of car B relative to the ground. Can you see I switched the order of the indices, but I'm still adding, but now I'm going to add the oppositely directed vector. So this right here, the velocity of car A relative to the ground, here is car A, and it is traveling 50 miles per hour with respect to the ground towards the south. So this is 50 miles per hour south. That's the velocity of car A with respect to the ground. And we're going to add on the opposite of the velocity of car B. Here's car B relative to the ground. So it's 70 miles per hour. But car B relative to the ground is heading northbound. Right? And so now you can see what's about to happen, right? So this is 50 miles per hour south plus, so the opposite of heading 70 miles per hour north is heading 70 miles per hour south. So these are both vectors that point south. So I can just add their magnitudes and they're going to add in the same direction. So 70 plus 50 is 120 miles per hour, which matches our gut instinct that A travels past B very fast, right? Faster than 50 or 70. It turns out that A travels past B at 50 plus 70. And what's more is we get the vector direction. So the velocity of car A relative to B is 120 miles per hour southbound. And secretly, we also know that velocity of car B as viewed from car A is the opposite. It's 120 miles per hour north. Okay, so let me point out something that's pretty important. This is a big note, that all of the above, all relative motion, right, is independent. Or actually, let me be careful because not everybody uses the word motion the same way. So all relative velocity is independent of relative location. Right? This is kind of a big idea. If we talk about relative location, we could maybe do something like this. Here is an arrow that points from B to A. And we might say that this arrow is a vector that locates A relative to B. That is, there is a position vector, and this position vector is the position vector that this little person in car B uses to locate the car A at this particular instant in time, right? Because you know that this vector right here is going to change as A passes by B and B passes by A. At some point, the arrow will point straight across, and at some later point, the arrow will point down to the left, right? But at this moment in time, the position, relative position of car A relative to B, or as measured by B, is that particular arrow right there. Yeah. So let's say that, so this is kind of a separate topic talking about relative location. So just this is a notation or an organization way of keeping track of what we're talking about. So this is a vector. It is the position of A as measured or relative to, as measured by car B, right? So this is what R sub AB stands for. And also note that if I want to ask, well, where does car A point to car B, right? This is the position of car B relative to A, and it is in the opposite direction to where B thinks A is, right? So this is also true. Also note, and this is a really interesting comment, that, for example, the velocity of x relative to y is equal to the time derivative of the position vector of x relative to y, right? This is a nice thing right here. And also note, also, what do you think is what I'm going to write down if I take two time derivatives? The acceleration of x relative to y is two time derivatives of the position of x relative to y. And of course, the acceleration vector, it is a vector. All right. So this is pretty cool. Yeah, so for example, check this out. So we can write down some arrows. Can you see that this arrow right here, the arrow that points from B to A, is equal to the arrow that points from B to C plus the arrow that points from C to A, right? Let me write this over here. That is, the arrow that points from A to B is equal to the arrow that points from B to C plus, right, the arrow that points from C to A. Oops, and I just blew, sorry, I just blew what I was trying to say. Actually, this is actually quite instructive. So this is the position of A relative to B, right? This arrow here is the position of C relative to B. Right? This arrow is the position of C relative to B, right? The order of the indices matters. And this is the position of A relative to C. So be very careful. Okay, so I just made that mistake in front of you. So let's rewrite this. This is, so the position of A relative to B is equal to the position of A. So I'm just going to switch the order. It doesn't matter, right, which one you add first. So it's the position of A relative to C plus the position of C relative to B. And I hope you can see that this matches or looks like our velocity addition formula from earlier. The velocity of A relative to B equals the velocity of A relative to C, so we're making x equal to C, plus the velocity of C relative to b. And if you take this relationship and you just take d by dt of both sides, so if these are equal, then the time derivative of the left-hand side is equal to the time derivative of the right-hand side, and that's simply what you get there.